Good morning, students. Just after the completion of the chapter D block elements, next switch over to another chapter, that is group 18 elements or noble gases. Group 18 elements, or it is known as noble gases. In the previous class, I completed the D block element. In that case, I give a preliminary idea about the long form of the periodic table. That is, the long form of the periodic table or the extended form of the periodic table is subdivided into 4 divisions known as S block, P block, D block and F block, depending upon the electronic configuration, whether the last electron enter to S orbital or P orbital or D or F orbital. So left side of the periodic table is known as S block, right side of the periodic table is known as P block, in between S and P block that is known as D block, and at the bottom of the periodic table that is known as F block. Mark that. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and it is known as, last one is 18. Mark that. This is known as S block. S block, it is known as P block, it is known as D block, and the last one is known as F block. 2 series are there. One is known as lanthanide series and one is known as actinide series. So in group 18 the elements are helium, neon, argon, krypton, genon and radon. These monoatomic gases constitute a family that is known as group 18 elements. They are colorless, odorless gases. They are known as group 18 element. These gases are also known as gases of atmosphere because they are available in the atmosphere. They are also known as rare gases or aerogens because their availability in atmosphere is low. Due to their stable configuration, the common electronic configuration, outer electronic configuration of noble gas is NH2 NP6. That means the electron enter into the valence shell are complete one. Due to their complete electronic configuration, they have the no tendency either to lose or gain electron. That's why they are also known as inert gases. But recently, many compounds of the noble gases, especially krypton and genon, have been synthesized. That's why nowadays these are known as noble gases instead of inert gases. Hence, the group 18 elements are known as rare gases, gases of atmosphere, inert gases, and also noble gases. Next we discuss about their common electronic configuration and source. Next we discuss electronic configuration. If we discuss the electronic configuration of noble gases, it has been observed that all of them except helium possess a common electronic configuration of NH2 NP6. Except helium, atomic number 2, that is 1s2. Rest, in case of neon, that is NH2 NP6, that means 2s2 2p6, 3s2 3p6, 4s2 4p6, 5s2 5p6, 6s2 6p6. In general, they possess NH2 NP6. That means they have 8 electrons in their valency shell. They complete their octet, except helium, they complete its duplet. Due to complete electronic configuration, due to stable electronic configuration, they have no tendency to either lose electron or gain electron. That's why they never came in contact, they never ready to combine with each other to go through the chemical combination. That's why they are noble or inert. Next we discuss their source of availability. Sources of availability. They are available from different sources. The sources are: point 1, atmosphere; natural gases; mineral and spring water; sun's atmosphere; radioactive element. They are the different sources of noble gases. Mark that point 1 is atmosphere. Except radon, which is a radioactive nature, all other noble gases are available to a lesser extent in the atmosphere. And among them, argon is the one which availability is a maximum among all the noble gases. Next one is natural gases. Natural gases also contain a lesser amount of helium. Next, mineral, that is monazite sand, and contain mainly little amount of helium, and also spring water also contain little amount of helium and argon. Next one is sun's atmosphere. Inside the sun, we know there is a process going on that is known as nuclear fusion. In this process, 4 hydrogen nuclei fuse together to form helium nucleus with the liberation of huge amount of energy. That's why sun is known as source of energy. So in sun's atmosphere, helium is available. Next one is radioactive element, that is the radon is this radioactive element. The radon is found in radioactive element, that is a radioactive disintegration of radium. I repeat again, the different sources of noble gases are atmosphere, natural gases, mineral and spring water, sun's atmosphere, and a radioactive element, that is a radium. undergoes radioactive disintegration to give the radioactive element, that is radon. Next we discuss the general trends in periodic properties. Next we discuss general trends in periodic properties. So many periodic properties are there, we discuss one by one. The different properties are monoatomic nature. Next, atomic radii. Next, ionization energy. Next, electron affinity. Next, melting and boiling point. Next, solubility. Next, liquefaction. And last one is adsorption capacity. Let us discuss one by one. These are some periodic properties. First one is monoatomic nature. So from the electronic configuration, it is clear that they have the stable electronic configuration, that is NS2, NP6. That means they obey the octet. They have 8 electrons in their valence shell. They have no tendency to lose or gain electron. That's why they are monoatomic in nature. They are colorless, odorless gases, monoatomic gases. And this monoatomicity is verified from the Cp by Cv ratio. We know that for monoatomic gases, Cp by Cv is equal to 1.66. Specific heat, constant pressure, and by specific heat at a constant volume is 1.66 for monoatomic gases. So from this value also it is clear that noble gases are monoatomic in nature. Next point is atomic radii. If we observe the atomic radii of noble gases in each period, then they have possessed the largest atomic radii across each period. It is because the atomic radii of noble gases is expressed measured in terms of van der Waals radii, while other atomic radii are expressed in terms of covalent radii. And by definition, we know that van der Waals radii is greater than that of the covalent radii. That's why in each period of the noble gases, in each period of the periodic table, noble gases possess largest amount of atomic radii. Next one is ionization energy. What is ionization energy? We know that it is defined as the amount of energy required. It is defined as the amount of energy required to remove the valence electron of a monovalent gaseous atom in order to form a positive monovalent positive ion or cation. We know that due to their stable electronic configuration, they have maximum value of ionization energy. However, if we moving down the group from helium to radon, then their ionization energy value gradually decreases due to increase in nuclear charge and also shielding effect. Next we discuss about electron affinity. What do you mean by electron affinity? Two definitions are there. One definition, it is defined as the amount of energy released when an extra electron added to a gaseous neutral gaseous atom in order to form a monovalent negative ion or anion. Another definition, it is a tendency to attract electron towards itself is known as electron affinity. So due to stable electronic configuration, they have no tendency to accept an additional electron. So noble gases possess zero electron affinity. They possess highest ionization energy. On the other hand, they possess zero electron affinity. Next property, melting point and boiling point. Due to their monoatomic nature, due to the presence of weak van der Waals forces of attraction, they have low value of melting and boiling point. However, this value gradually increases on moving down the group, because on moving down the group, atomic number increases, atomic size increases, magnitude of van der Waals force increases, as a result of which the value of melting point and boiling point increases on moving down the group. Next point, solubility. Solubility. Noble gases generally insoluble in usual solvent, that is water. However, they are easily soluble in organic solvent. Next one is liquefaction. Liquefaction. Due to the presence of weak van der Waals forces of attraction, noble gases liquefy with difficulty. I repeat again. Due to the presence of weak van der Waals forces, noble gases liquefy with difficulty. However, this value gradually increases on moving down the group, as on moving down the group due to increase in atomic number, increase in magnitude of van der Waals forces. Next point is absorption capacity. Except helium, other noble gases absorb. Except helium, all other noble gases absorb on charcoal, silica gel. These are the general trends in periodic property. Then we go through the general trends in chemical property or reactivity. Reactivity. General trends in chemical property or reactivity. Noble gases are monoatomic, colorless, odorless gases. They have practically zero chemical reactivity due to the following points. 2 to 3 points are there. That is, point 1 is stable electronic configuration. They obey octet rule. Point 2, they have high ionization energy. Point 3. They have zero electron affinity. Due to this character, they have no tendency to lose or gain electron. They never enter into the chemical combination. I repeat again. Some points are there. Point 1 is they have stable electronic configuration, that is NH2MP6. Next, they have high ionization energy. Next, they have zero electron affinity. Due to this property, they have no tendency to lose or gain electron. That's why generally they are chemically inactive. However, nowadays, many compound of noble gases, especially Krypton and Genon, has been synthesized. The first noble gas compound discovered by Barth in 1962, and the compound is XEPTF6. Mark that. Discovered by Bartlett in 1962, the first noble gas compound XEPTF6. Due to this, later on, instead of saying inert gases, they are known as noble gases. Next, we discuss about the compounds of Genon. In our syllabus, 3 compounds are there. That is, one is Genon difluoride, Genon tetrafluoride, and Genome Hexafluoride. Let us discuss one by one. Next, we discuss compounds of Genon. First, we discuss Genon difluoride, XCF2. Point 1, method of preparation. When a mixture of Genon and a fluorine, 1:2 ratio, taken in a nickel vessel and exposed to UV radiation, then Genon difluoride is formed. Mark the equation. That is Genon plus fluorine in the nickel vessel in presence of UV radiation. Genon difluoride is formed. I repeat again. When a mixture of Genon and fluorine 1:2 ratio are taken in nickel vessel and exposed to UV radiation, Genon difluoride is formed. Then we discuss about the physical and chemical properties. It is a generally colorless crystalline white solid. It oxidizes. The important 2 property possess. One is oxidizing nature, one is fluorinating nature. It oxidizes hydrogen to hydrogen fluoride. Mark that. Point 1. It oxidizes hydrogen to hydrogen fluoride. HCF2 plus H2 give rise to Hc plus HF. Point 2. It oxidizes hydrochloric acid to chlorine. Mark that. HCF2 plus HCl give rise to Hc plus HF plus Cl2. It oxidizes, I repeat again, it oxidizes hydrogen to hydrogen chloride. It oxidizes hydrogen chloride to chlorine. Next. It oxidizes water to oxygen. HCF2 plus H2O give rise to Hc plus HF plus O2. These are some chemical property oxidizing nature of hydrogen chloride. Next we discuss about their structure. Next we discuss structure, that is hybridization. If you observe the Genon atomic number 54, the outermost electronic configuration 5s2, 5p6, 5d0. If we go through the box-like diagram in the ground state, box-like diagram in ground state, 5s, 5p, it is 5s, 5p, it is 5d, 2, 6. First excited state, electronic configuration. That means one electron from p subshell jump to d subshell. Mark that box-like diagram. It is 2, it is 5s, 5p, 5d. So 1s orbital, 3p orbital and 1d orbital intermix to form sp3d hybridization. I repeat again, mark that 1s orbital, 3p orbital and 1d orbital intermix to form 5sp3d hybridization, in which 3 lone pair electrons are there, 3 lone pair electrons are there and 2 unpaired electrons are there. These 2 unpaired electrons overlap with the fluorine forming 2 bond pair. So the expected structure, that is Genon, mark that. It is a structure, that is a linear structure. Linear structure of Genon dichloride having hybridization sp3d hybridization, where it possesses 3 lone pair and 2 bond pair, 3 lone pair electrons, 2 bond pair electrons. Hybridization is sp3d and geometry is linear structure for xenon dichloride. And the uses of xenon dichloride, it is used as uses, under the uses 2 points are there. Uses 2 points are there. That is, it acts as an oxidizing agent. And point 2, it acts as a fluorinating agent. This is the little idea about the method of preparation, physical, chemical property, structure, that is hybridization, and uses of xenon dichloride. Next we switch over to method of preparation of xenon tetrafluoride. Next compound is xenon tetrafluoride. Method of preparation. Method of preparation of xenon tetrafluoride. When a mixture of xenon and fluorine in the ratio 1:5 is taken in a nickel vessel and heated to 573 Kelvin under 6 atmospheric pressure and then sudden cooling, we have xenon tetrafluoride. I repeat again. When a mixture of xenon and fluorine in the ratio of 1:5 is taken in a nickel vessel and heated up to 573 Kelvin under 6 atmospheric pressure and sudden cooling, we get xenon tetrafluoride. Mark the equation. Xc plus 2F2, 573 Kelvin, 6 atm pressure on sudden cooling, we get HCF4. Next, switch over to the general trends in properties. General physical and chemical property. Like xenon dichloride, it is also a colorless crystalline solid. Like xenon dichloride, it also acts as an oxidizing agent. It oxidizes hydrogen to hydrogen fluoride. It oxidizes hydrogen chloride to chlorine. Mark that. Point 1. It oxidizes hydrogen to hydrogen fluoride. HCl4 plus H2 give rise to Hc plus HF. It oxidizes hydrochloric acid to chlorine, that is HCl4 plus HCl give rise to Hc plus HF plus Cl2. It combines with water. To form xenon trioxide XCO3, HCl4 plus H2O give rise to Hc plus HF plus F2 plus XCO3. These are some chemical properties of xenon tetrafluoride. I repeat again. It oxidizes hydrogen to hydrogen chloride. It oxidizes hydrogen chloride to chlorine. It oxidizes water. It combines with water to form xenon trioxide. Then we discuss about the hybridization or structure of a xenon tetrafluoride. Then structure, we know that xenon, atomic number 54, the outermost electronic configuration, that is 5s2, 5p6, 5d0. The box-like diagram is is 5s, 5p, 5d. It is known as ground state, box-like diagram. Then on excitation, one electron from the p subshell jump to d subshell. That is known as a fast excited state electronic configuration. That is 5s, 5p, 5d, 5s, 5p, 5d, 1, 2, 3, 4, 5, 6, 2 unpaired electron. Again on excitation, one electron of paired 5p subshell jump to 5d. That is known as second excited state electronic configuration. That means 5s, 5p, 5d. It is 5s, 5p, 5d. 1, 2, 3, 4. That means 4 unpaired electron. So 1 5s, 3 5p, and 2 5d orbital get intermixed to form sp3d2 hybridization. I repeat again. 1 s orbital, 3 p orbital, and 2 d orbital involved in the hybridization to form resulting 6 sp3d2 hybridized orbitals, in which they possess 2 lone pair of electron and 4 unpaired electron. These 4 unpaired electron overlap with 4 unpaired electron of fluorine atom, forming 4 bond pairs. Mark that. This is known as lone pair electrons. The geometry is square planar. That means here number of lone pair electrons is equal to two lone pair, number of bond pair electrons 4, hybridization sp3d2, geometry, that is square planar. It is the idea about Genon tetrafluoride. Here two lone pair electrons are there. 4 bond pair, it is bond pair, 4 bond pair electron is there. Hybridization is sp3d2 and the geometry is square planar. And it also uses as an oxidizing agent. It is about the method of evaporation, physical, chemical property, hybridization, that is structure, and uses of Genon tetrafluoride. Next switch over to the method of evaporation of next compound of Genon, that is Genome Hexafluoride. Next compound is Genome Hexafluoride. Method of preparation. When a mixture of Genon and fluorine, the ratio 1:20, taken in a nickel vessel, and heated up to 533 Kelvin, 533 Kelvin, Genome hexafluoride is formed. I repeat again. When a mixture of Genon and fluorine is the ratio 1:20, taken in a nickel vessel and heated up to 533 Kelvin, then we get Genome hexafluoride. Mark the equation. 533 Kelvin under pressure, we have Genome hexafluoride. Next we discuss some trends in physical and chemical property. General properties. It is also a white crystalline solid. Like Genon difluoride, Genon tetrafluoride, it also oxidizes hydrogen to hydrogen fluoride. Mark that. Point 1. It oxidizes hydrogen to hydrogen fluoride. HCF6 plus H2 give rise to Hc plus HF. It combines with water. And the final product of hydrolysis is xenon trioxide. It reacts with water with 1 molecule, 2 molecule, 3 molecule. When it reacts with water with 1 molecule and 2 molecule, that is known as a partial hydrolysis. When it reacts with 3 water molecule, known as a complete hydrolysis. And in complete hydrolysis, it is formed xenon trioxide. Mark that. The required equation HCF6 plus H2O give rise to HCOF4 plus HF. HCF6 plus 2H2O give rise to HCO2F2 plus 4HF. Last one is HCF6 plus 3 water give rise to HCO3 plus 6HF. These two is known as partial hydrolysis, and the last one is known as complete hydrolysis. It is very important to mark question for this chapter. What happens when Genome Hexafluoride undergoes complete hydrolysis? Answer. When Genome Hexafluoride undergoes complete hydrolysis, that is, Genon trioxide is formed. And also for this chapter, one mark question. How many number of lone pair electron and bond pair electron are present in Genome difluoride, Genome tetrafluoride and Genome hexafluoride? Another one mark important is that what is the expected geometry for Genome difluoride, Genome tetrafluoride and Genome hexafluoride? What type of hybridization involved in Genome difluoride, Genome tetrafluoride and Genome hexafluoride? It is all about the physical and chemical property. Next we discuss about the structure, that is hybridization observed in Genome hexafluoride. Next is structure. If we go through the ground state electronic configuration along with box-like diagram of a Genon, that is 5s2, 5p6, 5d0, the box diagram. Five S, 5p, 5d. Then on first excited state, electronic configuration, that is it is 5s, 5p, 5d. Next, on another excitation, that is known as second excited state, electronic configuration. It is 5s, 5p, 5d. Mark that. Again on excitation, that is known as third excited state. That is third excited state, electronic configuration. The box diagram is it is 5s, 5p, 5d. So from this box-like diagram, mark that 1 s orbital, 3 p orbital and 3 d orbital participate, intermix in the hybridization, resulting in the formation of sp3d3 hybridization. I repeat again. 1 s orbital, that is 5s, 3 p orbital, that is 5p, and 3d orbital, that is 5d orbital, get intermixed to form 7s sp3d3 hybridization, in which 1 is lone pair and 6 is unpaired electron. These 6 unpaired electron get overlap with unpaired electron of fluorine atom, forming the distorted octahedral geometry of the Genome Hexafluoride. Mark the structure. That is Xc F F F F F. It is known as lone pair electrons. That means here number of lone pairs electron is 1, number of lone pair 1, number of bond pair is equal to 6, hybridization is equal to sp3d3, and geometry is distorted octahedral. I repeat again. In F6, that is Genome Hexafluoride, number of lone pair is 1, number of bond pair is 6, hybridization is sp3d3, and the expected geometry is distorted octahedral. And also, like Genon difluoride, it is also used as an oxidizing agent. It is all about the method of preparation, properties, structure, and uses of Genon compound, that is Genon difluoride, Genon tetrafluoride, and Genome Hexafluoride. Next we switch over to the uses of noble gases, that is uses of helium, neon, argon, krypton, xenon, and radon, one by one. Among them, uses of helium and neon, especially important one for exam point of view. Uses of helium. 3 to 4 points are there. It is used due to non-combustibility. It is used in filling airships and balloons for meteorological observation. Another one, the sea diver, the scuba diver use mixture of helium and oxygen during the sea diving because of low solubility of helium in the blood. When the scuba diver came out from the deep sea, the pressure decreases. At that time, that means it will protect to diffuse the nitrogen, unless the sea diver felt a very, very painful sensation known as bends. So in order to overcome that painful sensation, the sea diver uses the mixture of helium and oxygen for respiration. Next, this helium-oxygen mixture also used by the patient suffering from a respiratory disease, that is asthma. Next, this helium also used for gas thermometer for recording low temperature measurement. This helium also used for improving inert atmosphere. These are some uses of helium. Next we discuss uses of neon. The most important uses, only one point of this one is, that is beacon light. Beacon light. It is used for navigation purposes as because it has the fog penetrating power. That's why it is used in navigation for purposes. Most important thing that one mark question, which noble gas is used in beacon light? That is neon. It is also used in neon sign. It is also used in neon sign tube for advertising purposes. It is also used in a fluorescent lamp. These are some uses of neon. Next we switch over to uses of argon. Uses of argon. Argon is used for improving inert atmosphere. It is also used in laboratory for handling the substances which are sensitive to heat and light. That is helium argon also used in neon sign tube for advertising purposes, for giving different glow. Next we go through the uses of krypton, genon and radon. Uses of krypton, genon and radon. There is one important uses of krypton, that is krypton 85, one isomer. Krypton 85 is used to detect the thickness of a metal sheet and a plastic sheet. I repeat again, the krypton 85, the isomer of krypton, is used to detect the thickness of a metal sheet and a plastic sheet. Krypton 85 also used for photography purposes. Radon is used for radioactive research. Radon is also used for treatment of cancer. Radon also used in the photography. These are some uses of noble gases. And also it is all about the chapter group 18 element or noble gas element.